Alrighty, y'all. Today we're taking a look at Recitation 20, question 2. And I know he said in class that we didn't go over this, but I read it in the textbook, so you guys can learn how to do it, I guess. So this has a circular loop with a current, a radius. The bottom half has a magnetic field that points into the page. Blah, blah, blah. What should the magnitude of the magnetic field be such that the magnetic force exactly balances the gravitational force? Right? So we have the mass of the loop. Right? So if we're calculating our gravitational force, that's going to be Fg. It's going straight down. And that's going to be our 1 kilogram times 9.81. Right? So when we're calculating our magnetic force so that it can directly balance this is when we're going to use an integral. Right? We're going to integrate from pi to 2 pi, or 0 to 2 pi, or 0 to pi, right? We're just getting half the circle. I'm just going pi to 2 pi, just so you get that bottom of the circle. And our equation, I, B, R, sine theta, right? And then, right, and that's d alpha. But we also have to multiply, because this is only going to give us magnitude. We have to multiply by a, what's going to give us the direction, right? So what's going to give us the direction is negative sine of alpha, right? Because as we go around, like if it's here, here's our alpha. We're going to be looking for the y component, all right? Because we have our symmetry in the x direction, right, where this would be canceling like that. Or here's the x direction of that, and here's the x direction of that. Like those, the same thing where that's symmetrical there, so they would just cancel out. And we're just looking for what's going to cancel out with our y direction here. So we're taking the sine of this, and I'm taking the negative sign because I'm going from, like, I'm taking the bottom half of the triangle, and I need it to equal a positive magnitude eventually. I don't know what happened to this, but oh, because I moved it, right? Sine theta. All right, so what I'm going to do is I'm going to start plugging in my numbers, right? So sine theta, our theta of our current, in between our current and the magnetic field, which is going into the page, and this is parallel to the page. So our angle between, that's going to be 90 degrees. Sine of 90 is just 1, so that's just going to disappear, right? So we're going to integrate, and we're setting this equal to the 9.81 that we calculated for our force due to gravity up here. Pi to 2 pi of our current was 2 amps, right? Yep. Times b, which is what we're solving for. Our radius was 1 meter. Right? That was a radius times negative sine alpha d alpha, right? So now we just integrate this real quick, and the only thing with an alpha in it is going to be this. Like, all of these are our constants. We can pull these out. So it's going to be 9.81 equals 2b, or negative 2b, integral pi to 2 pi of sine alpha d alpha. Integral of sine is going to be negative cosine, and that's also just going to get rid of our negative out here. Right, so it's going to be 2b cosine alpha evaluated from pi to 2 pi. That has to equal 9.81. All right, so we plug in our bounds over here. 9.81 equals 2b times cosine 2 pi minus cosine of pi. All right, cosine of 2 pi is 1. Cosine of pi is negative 1. Right? So that's going to end up being a 1 plus 1, 2, 2 multiplied in, 9.81, sorry. So 9.81 is going to equal 4 times B, which again, B is our magnitude of the magnetic field. So you're just going to solve this out real quick. That's going to give you your answer in Teslas, again, because everything's still in base units. All right, so I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this problem or any other problem that you want me to try to explain, and I will do my best to try to explain it, because I guess Sydney explains stuff.